Good day, students. Hope you're keeping safe. You're welcome to Golden Line School online physics class. Now, our topic we'll be looking at today will be refraction. Another refraction we'll be looking at real depth and apparent depth. Now, our learning objective today are definition of refraction, laws of refraction, real depth and apparent depth, and we'll be looking at some calculations on real depth and apparent depth. Now, what is refraction? Now, refraction is defined as the bending of light ray as it travels from a medium of one density to another density. So that means refraction always occurs when light ray travels from one medium to another medium. Let's say, for example, you have light traveling from air to water. Now, the light ray tends to bend as a result of refraction. Now, if you look at the diagram on the board, you have light traveling from air to water. Also, light can also travel from air to glass, or it can travel from water to glass, depending on the medium that light is traveling. But for us to have the phenomenon refraction, light must always travel from one density to another density. Now, let us look at the laws of refraction. Now, there are two laws of refraction. Now, the first law states that the incident ray, which is this ray in this place, the refracted ray, which is this, and the normal all lie on the same plane. Now, this is the normal. The dashed line here represents the normal. So, if you look at it, the incident ray, the refracted ray, and the normal all lie on the same plane. That means they meet at a point. Now, that is the first law of refraction. Now, to the second law of refraction. Now, the second law of refraction is also called Snell's law. Let me come again. This is also the second law of refraction is also called Snell's law. Now, what is Snell's law? What does it state? Now, Snell's law states that the ratio of the sine of angle of incidence to the sine of the angle of refraction is equal to a constant called refractive index. So that brings us to refractive index. Now, according to the second law, the refractive index n is equal to sine I, that is, I represents the angle of incidence, all over sine r represents the angle of refraction. Now, so this refractive index is equal to sine I all over sine r. Now, let us now go to real depth and apparent depth. Now, what is real depth and what is apparent depth? Now, for the real depth and apparent depth, now let us look at a case study where you have a man swimming inside a swimming pool. Now, if you look inside the swimming pool, you notice that the man appears to be shallow than where he is actually is. Now, that is because of refraction tends to bring the height of the man up, although the man is at the base of the swimming pool. Now, also, when you have a glass, for example, and then you place a coin under the glass, it will look as if the coin came up. But that side you are seeing is not the actual place where the coin is. It is because of refraction. Refraction can be deceiving. So, the height of the coin or of the man in the swimming pool, in that case I mentioned you are seeing, is called the apparent depth. Now, why the main depth of the man or the coin, when it is measured with a ruler, is called the real depth. So, let me give you a diagram on the board. Now, let's say you have something like this. You have a cylinder, and then you have water in it, and then you place a coin inside it. Now, you will notice that the coin, when you observe the coin from this place, you notice that the coin might appear here. Okay? So, this place you are seeing the coin is called the apparent depth. So, let's call it from here to here, let's call it D. Now, why this place, from this place to where the water is, capital D, is called the real depth. So the real depth is the actual position of the coin, while the apparent depth is the one that is deceiving. Now, according to Snell's law, we can get a formula for real depth and apparent depth. Now, we can relate real depth, apparent depth, and refractive index. Using the formula, your refractive index is equal to real depth all over apparent depth. Okay? So refractive index is equal to real depth all over apparent depth. Now, let us look at few examples on the board. Now, look at this. Now, if you look at this example on the board, you have what is the apparent depth of a tank 3 meters deep. Now, the tank is 3 meters deep when viewed outside. Now, if you have, for example, a tank, and then this is the depth of the tank from here to here is 3 meters. Now, they said when viewed outside, that what will be the what? What will be the depth of the tank? Now, this is the real depth of the tank, D. Now, of course, when you look at the tank, you will observe that the base of the tank will not actually be 3 meters because of refraction. So let's say it was somewhere here. Now, that means from here to here, this is where the water is. From here to here is 3 meters. Now, so the apparent depth is going to be from here, this point, to this point. So let's call the apparent depth small letter d. So from this place, our apparent depth is an unknown value. So using the formula connecting the real depth, apparent depth, and the refractive index, we say the refractive index is equal to real depth all over apparent depth. So therefore, the refractive index from this question, because you're giving water, refractive index is 1.33, so you have 1.33 is equal to your real depth, which is the depth of the tank, as 3, all over, you have your apparent depth d, which is unknown. So from this place, you cross multiply, so d times 1.33 is equal to 3, so divided by 1.33 divided by 1.33, so this cancels this. So your apparent depth is equal to 3 divided by 1.33. Now, if you divide it, you are going to get 2.26 meters. So you can see that the real depth is always larger than the apparent depth. So that is your number 1. Now, let's look at this example 2 on the board. Now, you have a glass block 3.0 centimeter thick. That means you have a block which is 3.0 centimeter thick. It's placed over a coin. Of course, just like you have a block and then under it you place a coin. Of course, if from here, let me make it larger. This is the coin. Now, from here to here is 3 meters. That is the real depth. Now, if you look at the coin, it will appear shallower. Now, so that from this position to this place is your apparent depth, which is small d. Now, they say it's placed over a coin. Calculate the depth which an observer will view. Now, from the question, they said an observer will view. That is the apparent depth. Given the refractive index of glass as 1.54. Now, from this place, go back to your formula. N is equal to real depth, capital letter D, all over apparent depth, small letter d. So your refractive index in this place is 1.54 is equal to your real depth, which is 3, all over your apparent depth, which is x, small letter d, you don't know. So you cross multiply, so d becomes equal to, you have 3 divided by 1.54 when you make d subject of the formula. Now, if you divide this, now this will give you 1.948 meters, or approximately 1.95 meters. So you can see that is how we get the real depth or the apparent depth. So at this juncture, Hope you all understand what real depth and apparent depth is all about. Alright, thank you very much for listening. Now, I have posted my notes on the IS Golden Line ISM platform. Now, do ensure you read the notes, and you can go on WhatsApp, send me your comments and your questions on this video and on this topic. So I hope to see you next time. Thank you.